So it was hypobromous acid or something like that. It was HBRO or something. What was it?
It was C9H13 and then N.
Wait, what? I guess I don't know. What does it look like? Find the pH. Oh, C9H13. Oh, are you looking at 20 or 19?
20 for this one.
Oh, you're looking at 20.
Wait, which one?
Were you looking at this one or this one?
Let's do 19 and
You want to do 19? Oh, okay, both. Okay, so hypobromous acid. Okay, so we're trying to find hypobromous. I've never seen it, so I'm trying to figure out what it is. Hypobromous acid. Okay, so we're trying to find the percent ionization. I don't know if that's how you spell ionization. Is it an I or an O? Ionization. Okay. Percent ionization, the pH, and the concentration of all species. Okay. pH and concentration of all species. Okay. Okay, kind of tell me a little bit about how you've tried approaching it.
Well, we learned about this today, and
okay.
I would think since it says concentration of all species, you're going to have a reaction.
Good.
And so we're going to want to draw this at equilibrium. And if this is hydrobromic acid and in aqueous solution, the only thing I can think of is adding it to water.
Yes.
And then when we add it to water, it's going to become, we're going to have a hydronium ion, and then we're going to have just
Hypobromous.
bromus.
Does this have a charge?
Yes, it has a negative charge.
A negative
it
charge.
Lost the,
Good. A
lost
proton.
the proton.
Good.
And it's both ways because we have a weak acid.
So this is, what did you say this in relation to this is?
That is going to be its conjugate base, which means it's going to be a stronger conjugate base because it is a weak acid.
Well, it could be. Now, we don't, when it comes to weaks, one thing you have to keep in mind is it's uncertain unless we have their K values.
Okay, but if we can imagine that it would be stronger, a stronger
Perhaps.
base.
Because this could be a really, really, really weak base or weak acid. Or this could be a stronger acid. We don't know. Because this is, when it comes to weaks, it's really hazy. So it is good. Keep that in mind, the inverse relationship, right? But it's still hazy that you can't go, oh, this is weak. That means this is strong. No, you can't do that. You'd say this is weak. This is also a weak base. Is this one stronger or this one stronger? I don't know. You have to look at the Ks.
Okay, that makes sense.
Does that make sense?
Yeah. I was trying to picture it on the table where like if the strength of the bases are increasing as you go down and the strength of the acids are increasing as you go up.
Right.
So your conjugate base is proportional.
Well, it's inversely
proportional to the strength of the acid.
Yes.
Okay.
Yes, you have that perfect.
Okay.
Keep that in mind. That's very, very important. But once again, remember that when they're both weaks, the assumption can't quite be made unless you know already what the strength is. Like, unless you have seen the value and you haven't memorized or something. I don't know. You don't have to do that, by the way. But
now, okay.
Okay, go ahead. Continue.
And then, so now that we have this reaction, we know that the percent ionization is going to be the initial concentration of our. No. It's going to be the final the total concentration of the hydronium ion.
Well, what's going to be that? Say that one more time. I just want to make sure I follow what you're saying.
So we're going to divide the initial concentration of the hydronium ion, or the final concentration of the hydronium ion, by the initial concentration of the acid.
Almost. Now you have that in mind, the idea where you have, we have products over reactants. You're thinking of the equilibrium expression, aren't you? You're thinking of...
I thought it was percent ionization, but I could be saying it wrong.
Okay, how about this? I'll give you a good strategy.
Okay.
So, I like how you were thinking. okay, we have this idea where we have an acid and we have it in water, right? So we have this liquid. And a quick question, are these, what should their states be? What should I have right here?
Aqueous.
Yeah, little aqueuses, yeah. Little AQs. Okay, so we know that this is in water. Now, here's a thought. How come it dissociates?
Because it's a weak acid.
Mhm.
And weak acids dissociate because I want to say that the bond between the hydrogen and the bromide is weak, and so
Yeah.
it's going to lose its proton easier.
Yes, it's weak enough that it can break, because if it's a weak acid, that means the strength of the bond between the H and the Br is a little bit stronger than what a strong acid would be. Because a strong acid just lets go of that H real quick, which means it's almost like he doesn't even necessarily want to hold it, right? So the bond, the strength between the H and the anion of a strong acid is relatively weak, like this. The bond between these right here with these two electrons is not very strong. So this guy could let it go and be fine hanging out like this. Right? With this negative charge on one of these. Don't know 100% how that works, but.
And it's a strong acid because it wants to donate protons.
Right. Yes, it wants to donate this H.
So the
But
strength is determined by how easily it donates the H.
yes, which also correlates with a weak bond between the H and the compound.